All right, so this video is just going to go through this practice example problem where basically what we have is we have two space probes. We're going to have probe A and probe B. The first space probe is going to geostationary orbit directly above Jupiter's equator. So imagine this, like here's my north pole of equator right here, right? And so we're kind of looking down at it. And probe A is going to move around like this. Probe B is on the planet itself and it's going to move around like that. Okay, even though, and I understand, the surface of Jupiter is up for debate, right? If it's a gas giant, is there really ever a surface that you could be on? But just for the sake of the problem, here's what it is. Which probe, if either, has a greater speed? Justify your answer. So the speed is distance over time, and because this, basically what you could think of it as, B and A make one complete rotation in the same amount of time, okay? If A is geostationary above Jupiter's equator, then basically as Jupiter spins around one time, this probe is always going to be above it, right? So at this point, if this is where B is, A is right here. If B is here, A is right there. So they're going to make one rotation in the same amount of time. So speed then is distance divided by time. Distance is going to be my circumference of this circular path that I create, which is 2 pi r. And because we know r of A is greater than r of B, then we can say that A has a greater speed than B is going to be. It's going to cover a greater amount of distance in an equal amount of time. Second part then, which probe, if either, has the greatest acceleration toward the center of Jupiter? So that is a centripetal acceleration, and centripetal acceleration is, again, velocity squared divided by r. So my velocity is just this idea, right? But my velocity, again, is changing every second. So velocity is this way, and then it's this way, and then it's this way. So it's not the speed of which is changing, it's simply the direction, and that's why my velocity is changing. So that speed, which we calculate here, is the magnitude of my velocity here. So v squared over r, I'm going to simplify that out, or write that out as 2 pi r over t is my velocity divided by r. We're going to square the top, so that gives me 4 pi squared r squared divided by t squared. Now what's going to happen is this r here is going to cancel out with one of the r squareds at the top. So then my final acceleration centripetal is 4 pi squared r over t squared. So that means that, again, A has a greater centripetal acceleration than B. If it's simply based on, 4, pi, and t are all the same. So clearly what we can see is that the bigger the radius, the bigger the centripetal acceleration, right? AC equals 4 pi squared r over t. Okay, so the bigger the r, the bigger the AC. The last part then deals with consider the list of gravitational forces below. And it's a combination of all the forces that are acting. You have the force Jupiter on probe A, Jupiter on B, probe A on Jupiter, probe B on Jupiter, and then the forces of the probes on each other. Okay, so here's how we're going to look at that. So here's what I said. The force is going to be calculated by gmm over r squared, right? And then, so here's, the first thing I said was 2 is greater than 1, right? So the force on probe B is greater than the force on probe A. The masses are the same. So mass A and mass B are the same, right? But this is an inverse squared relationship. So the closer that B is to Jupiter, the bigger the force is going to be. So what I said was that 2 is greater than 1. And then the other justification is basically Newton's third law. Newton's third law, which basically said for every action there is an equal and opposite reaction. So if Jupiter pulls on probe A pulls on Jupiter. Equal and opposite. If Jupiter pulls on B with a larger force, B pulls on Jupiter. Right? Equal and opposite. And if A pulls on B, then B pulls on A. Equal and opposite. Right? So here's what I said. The forces on probe B are going to be the greatest, and it's going to equal that of B on Jupiter. So 2 and 4 are the same. They are bigger than 1 and 3, which is the force of Jupiter on probe A. These are less than this because it has a bigger distance away. And then because the masses of the probes are substantially smaller than the masses of Jupiter, right, those forces on each other are going to be the same, but they're going to be less than the other.